Most of us met physics through one equation: force equals mass times acceleration. Push something, it accelerates. That's mechanics, that's the whole game. And it works. You can send probes to other planets with it. But there's a completely different way to do all of mechanics, one that doesn't start with forces at all. It starts with an almost philosophical-sounding idea, that of all the paths a system could possibly take, nature picks the one that makes a certain quantity as small as possible. It's called the principle of least action, and it's arguably deeper than Newton. It's the language every modern theory of physics is actually written in. George, I want to genuinely understand this, not just nod at it. Why would you ever abandon force equals mass times acceleration for something that sounds like nature has a preference?
Because force equals mass times acceleration, for all its power, has some real practical pain built into it, and chasing the fix for that pain leads you somewhere astonishingly deep. So here's the plan for our time together. First, I'll show you exactly where Newton's approach gets clumsy. Not wrong, clumsy. So you feel why anyone went looking for something better. Then we'll build the new object at the center of this whole framework called the Lagrangian, which is startlingly simple. Then we'll state the principle of least action itself and see what it means. Then we'll turn the crank and watch it reproduce Newton's law exactly, so you trust it, and then watch it do something Newton's law makes painful, easily, which is the real payoff. And finally, we'll follow the idea outward to see why it, and not force, turns out to be how the deepest physics is written. 2 ingredients, a quantity called the action and the rule that nature makes it stationary, and all of mechanics reorganizes itself.
Start with the pain then. Force equals mass times acceleration sends probes to Mars. Where does it get clumsy?
It gets clumsy the moment your problem isn't a free particle flying through open space. Force is a vector. It has a direction, and acceleration is a vector, and the equation ties them together, component by component, in whatever coordinate directions you've chosen. Now imagine a bead threaded on a curved wire, forced to slide along that wire and nowhere else. To use force equals mass times acceleration, you have to worry about the force the wire itself exerts on the bead to keep it on track, a force that points sideways, perpendicular to the wire, whose only job is enforcing the constraint. You don't care about that force, it does no useful work, but you're stuck bookkeeping it, because it's part of the vector balance. And the more constrained and jointed your system, a double pendulum, a spinning top, beads on wires connected by rods, the more these constraint forces multiply and tangle, and the messier the vector equations become.
So the annoyance is all this machinery you have to track just to keep things on their rails, even though those constraint forces aren't what you actually care about.
Exactly. You're spending most of your effort on forces you have no interest in, purely to respect constraints. And there's a second, subtler clumsiness. Force equals mass times acceleration is written in a particular coordinate system, usually the straight x, y, z of ordinary space. But the natural way to describe a pendulum is by its angle, not its x and y. The natural way to describe a bead on a wire is by how far along the wire it slid. When you try to force those natural, curvy coordinates into the vector equation, calculus terms sprout everywhere and it becomes a headache. So you've got 2 pains: unwanted constraint forces and an awkward marriage to rectangular coordinates. The Lagrangian approach heals both at once, and the way it does it is to stop talking about forces and directions altogether and talk about energy instead.
Energy instead of force. Okay, that's already a big shift because energy is just a number, isn't it? It doesn't point anywhere.
That's the whole liberation, and you've put your finger on it. Energy is a scalar, a single number with no direction. Kinetic energy, the energy of motion, is just 1/2 times the mass times the speed squared. A number. Potential energy, the stored energy of position, how high you've lifted something, how far you've stretched a spring, is also just a number, and numbers are so much easier to work with than vectors because you don't have to track directions and components. You just add and subtract. So the Lagrangian approach makes a bet that you can capture all of mechanics using only these two energy numbers and never once draw a force arrow. And the central object, the Lagrangian, is almost shockingly simple given how much it does. You take the kinetic energy and you subtract the potential energy. That difference, kinetic minus potential, is the Lagrangian.
Wait, subtract? That's the part that always trips people up. Total energy is kinetic plus potential. That's the famous conserved quantity. Why on earth would the important object be kinetic minus potential? That seems almost perverse.
It is genuinely one of the strangest looking choices in physics, and you're right to stop on it. Because everyone's instinct is that the meaningful combination is the sum, the total energy. The minus sign feels wrong, and I'll be straight with you, there is no cheap one-sentence intuition that makes kinetic minus potential feel obvious. Its justification is that it works spectacularly, and we'll see it work. But here's a thread of intuition to hold. The total energy, kinetic plus potential, is about what a system has at one instant. The Lagrangian, kinetic minus potential, is about the tension between motion and position over a whole journey, how the system trades its motion against its place in the potential as it travels. It's less a snapshot and more a running character of the trip. Keep that loosely in mind. The real payoff is that this particular combination is the one whose accumulated total nature chooses to make stationary.
Accumulated total. So we don't just look at the Lagrangian at one moment. We add it up along the path.
We add it up along the entire path through time, and that accumulated total has a name, the action. Here's the picture. A system starts somewhere at some moment and ends somewhere else at a later moment. Between those two fixed endpoints, imagine every conceivable path it could take. Not just the real one, but all the imaginary ones, the ones where it wanders off and comes back, the ones where it speeds up and slows down absurdly. For each such path, you walk along it moment by moment, evaluate the Lagrangian, kinetic minus potential, at each instant, and add all those values up over the whole trip. That running sum, the Lagrangian totaled over the path in time, is the action of that path. Every conceivable path gets its own number, its own action.
So the action is a single number attached to a whole path, a way of scoring every possible way the system could have gone from start to finish.
That's precisely it. The action is a score for an entire history, one number summarizing a complete path from beginning to end. And now we can state the principle, the heart of everything. Of all those conceivable paths, each with its action score, the one that nature actually follows, the real physical motion, is the path whose action is stationary. For most ordinary situations, stationary means smallest. The true path is the one of least action. That's the principle of least action. Nature, out of all the ways it could get from here now to there then, takes the path that minimizes this accumulated kinetic minus potential.
Is there a familiar, everyday example where nature visibly takes the best path? Something I can picture before we trust the abstraction.
The cleanest one is light, and it's older than Lagrange. It's called Fermat's principle. Light traveling from one point to another takes the path that takes the least time. In empty space, that's just a straight line, nothing surprising. But watch what happens when light passes from air into water. It bends at the surface. That's refraction. Why bend? Because light travels slower in water, so the quickest route isn't the straight line. It pays to travel a bit farther in the fast medium, air, and less in the slow medium, water, kinking at the boundary to save time overall. It's exactly the problem a lifeguard faces when a swimmer is in trouble. You run fast on sand and swim slowly in water, so you don't head straight at them. You angle your run to spend more distance on the sand instinctively taking the least time path. Light does the same, and the precise bending angle that results is a law you may have learned in school, falling straight out of least time. So nature taking an economical path isn't exotic. You've seen it every time you noticed a straw looking bent where it enters a glass of water. Least action is that same idea, generalized from light's least time to the least action of any mechanical system.
That helps a lot. The bent straw is nature minimizing something right in front of me. Let me make sure I'm not romanticizing it, though. It sounds like you're saying the particle somehow surveys all possible futures, computes a score for each, and picks the cheapest. That can't be literally what's happening. A rock doesn't shop around.
You are absolutely right to be suspicious, and that suspicion is one of the most important instincts to have here, so let's not paper over it. We'll come back to it properly near the end, because there's a real and beautiful resolution. For now, hold it as a working slogan, not a literal claim about a rock deliberating. And let me clean up one word I've been loose with. I keep saying least, minimum, but the precise word is stationary. Stationary means if you nudge the path slightly, this way or that, the action doesn't change to first order. It's flat, like the top of a hill or the bottom of a valley, where a tiny step sideways doesn't change your height. Usually it's a genuine minimum, the bottom of a valley, which is why we say least action. But the exact, always true statement is that the true path is the one where the action is stationary, flat against small wiggles. That flatness is the mathematical condition we can actually compute with.
Okay, stationary. The action is flat, unchanging, against small nudges of the path, the way the bottom of a valley is flat. And I'm guessing that flatness condition is what you turn into an actual equation you can solve.
That is exactly the move, and it's one of the great pieces of mathematics, the calculus of variations. Ordinary calculus finds where a function is flat by setting its derivative to 0. That's how you find the bottom of a curve. The calculus of variations does the same trick, but for a whole path instead of a single point. It asks, what condition must a path satisfy so that the action is flat against every possible small wiggle of the path? And when you carefully work that out, demanding the action not change under any tiny deformation of the path, out pops a single clean equation that the true path must obey at every instant. It's called the Euler-Lagrange equation, and it is the engine of the entire framework.
Before you hand me the equation, you called this a whole branch of mathematics, the calculus of variations. Something must have forced people to invent it. Where did it come from?
It was born from a single gorgeous puzzle, late in the 1600s, and the story tells you exactly what the subject is for. A mathematician named Johann Bernoulli posed a challenge to the finest minds in Europe. Imagine a bead sliding down a wire from a high point to a lower point, off to the side, under gravity, with no friction. Question: what shape should the wire be so the bead gets from top to bottom in the least possible time? People's first guess is a straight line, shortest distance. But a straight line is slow to get started because the bead builds up speed lazily. What if you make the wire steep at the very beginning so the bead plunges and picks up speed fast, then levels out to use that speed? That head start might win, even though the total path is longer. The true answer, the curve of fastest descent, turns out to be a specific, graceful arc called a cycloid, the very curve a point on a rolling wheel traces. And notice what the question is. Out of all possible shapes, find the one that makes a quantity, here, the total time, as small as possible. That is not ordinary calculus, where you find the lowest point of a curve. You're searching over whole shapes, whole functions. A new kind of math was needed to answer it.
And I'm guessing the people who cracked that puzzle are the same names attached to this whole framework.
The very same, which is why the machinery carries their names. Legend has it, the challenge reached Isaac Newton one evening. He was not a young man and had a full day's work behind him, yet he solved it before going to bed and sent back the answer anonymously. And Bernoulli, seeing the elegance, is said to have remarked that he recognized the lion by its claw. Leonard Euler and Joseph Louis Lagrange then built the general theory, how to find the path that makes any accumulated quantity stationary, and that is precisely the Euler-Lagrange equation we're about to meet. Lagrange packaged the whole of mechanics in this language in the 1700s. A bit later, William Rowan Hamilton sharpened the underlying principle into the crisp statement of stationary action we've been using. So this isn't a modern repackaging of Newton for convenience. It's a parallel tradition, nearly as old, that grew from asking, which path is best, instead of, what force acts now? And the tool that answers every such question is the equation you asked for. Let me give it to you.
Can you give me the Euler-Lagrange equation in words? I want to actually hold it, even without symbols on a page.
I can, and it's more graspable than its reputation. Remember, the Lagrangian depends on two things about the system at each moment: where it is, its position, and how fast it's moving, its velocity. The Euler-Lagrange equation relates how the Lagrangian changes with respect to those two. In words, take how the Lagrangian changes as you change the velocity. That quantity turns out to be the momentum, and ask how it changes over time. That rate of change must equal how the Lagrangian changes as you change the position. Even more compactly, the time rate of change of the momentum equals the push coming from how the Lagrangian varies with position. And if that last sentence sounds suspiciously familiar, rate of change of momentum equals a push, hold that thought, because it should, and in a moment we'll see it literally become Newton's law.
Let's do that, because that's what would make me trust the whole apparatus. Show me the Euler-Lagrange equation turning back into force equals mass times acceleration for something simple.
Let's take the simplest real system. A single particle moving in one dimension under some potential. Say a ball in Earth's gravity, or a mass on a spring. Write its Lagrangian. Kinetic energy is 1/2 the mass times the velocity squared. Potential energy is whatever the potential is at the particle's position. The Lagrangian is the first minus the second. Now feed that into the Euler-Lagrange recipe. The first piece, how the Lagrangian changes with velocity, for the kinetic term, that's the mass times the velocity, which is exactly the momentum. Good. Now the equation says, take the time rate of change of that. The rate of change of mass times velocity is mass times acceleration. That's the left side. And the right side, how the Lagrangian changes with position. Only the potential energy depends on position, and the rate at which potential energy changes with position, with a minus sign, is precisely the definition of force. So the equation reads, mass times acceleration equals force. Newton's law, reproduced exactly, dropping straight out of make the action stationary.
That's genuinely satisfying. You didn't assume Newton, you derived him. The whole force equals mass times acceleration is just the special case of the Euler-Lagrange equation for a particle in a potential. So if it just gives back Newton, though, what have we actually gained? Same physics, more machinery.
If that were all it did, you'd be right to shrug. And this is the crucial turn. It gives back Newton, yes, but the way it gets there never once mentioned a direction, a vector, or a constraint force. The entire derivation used only energy scalars, and that means it doesn't care what coordinates you wrote the energies in. That is the superpower. Go back to our painful bead on a curved wire. In the Newtonian approach, you fought with sideways constraint forces. In the Lagrangian approach, you simply describe the bead's position by one number, how far along the wire it has slid. Write the kinetic and potential energy in terms of that one number, form the Lagrangian, and turn the Euler-Lagrange crank. The wire's constraint is baked in for free, because you only ever allowed the bead to move along the wire in the first place. The constraint forces you dreaded never appear, they're gone.
Oh, that's the payoff. Because you chose a coordinate that already lives on the wire, the constraint is automatic, and the annoying perpendicular forces never enter the calculation at all.
They never enter because you never described a motion that would violate the constraint. This is why physicists reach for the Lagrangian whenever a system has awkward geometry or constraints: pendulums, linkages, beads, rotating frames. You use what are called generalized coordinates, any convenient set of numbers that pin down the configuration, angles, distances along curves, whatever fits. And the beautiful fact is that the Euler-Lagrange equation has the exact same form in all of them. You don't rederive anything for a new coordinate system. Write the energies, form kinetic minus potential, apply the same crank. The method doesn't care whether you chose an angle or a distance or something exotic. That coordinate freedom, plus never touching constraint forces, is a colossal practical simplification.
Give me the pendulum concretely, because that's the classic case where I remember the Newtonian version being fiddly.
The pendulum is perfect. A mass on a rod of fixed length, swinging. In the Newtonian approach, you resolve gravity into components along and perpendicular to the rod, worry about the rod's tension, and it's a small chore. In the Lagrangian approach, you notice the only thing that can change is the angle the rod makes with vertical. One number, one generalized coordinate. The mass's speed is the length of the rod times how fast the angle is changing, so the kinetic energy is 1/2 the mass times that squared. The potential energy is just how high the mass is, which you can write from the angle. Form the Lagrangian, kinetic minus potential, apply Euler-Lagrange with respect to the angle, and out comes the pendulum's equation of motion directly. The rod's tension never appears because the rod's length is fixed, and you simply never allowed a motion that stretches it. One coordinate, two energies, turn the crank, done.
Can you give me a physical feel for what minimize kinetic minus potential actually does? Why that produces, say, the arc of a thrown ball?
It's worth building because it makes that strange minus sign do visible work. Toss a ball straight up and over. Its start point, its landing point, and the total time of flight are all fixed. Now the action is the accumulated kinetic minus potential. To make that small, the ball wants, loosely, two things at once: to move slowly, low kinetic energy, and to be high up, high potential energy, because we're subtracting the potential, so being high makes kinetic minus potential smaller. So the ball would love to leap up high and dawdle slowly near the top, where it's both high and slow. But it can't dawdle forever because the total time is fixed and it still has to reach the far end point. So there's a tension. Climb high to gain potential and slow down, but not so extravagantly that you have to race and build up costly kinetic energy during the rest of the trip. The exact compromise that balances those two urges, given the fixed endpoints and time, is precisely the parabola gravity actually produces. The familiar arc is the negotiated settlement between get high and go slow and don't run out of time. That's what minimizing kinetic minus potential feels like, physically.
That finally makes the minus sign feel like something rather than a trick. The ball is bribed to climb and slow, but taxed for having to hurry later. Does the energy language also make conservation laws easier, or just the equations of motion?
It makes them almost fall into your lap, and the rule is a little magical the first time you see it. Look at the Lagrangian for your system. If some coordinate doesn't actually appear in it, if only that coordinate's rate of change shows up, but not the coordinate itself, then the momentum associated with that coordinate is automatically conserved, constant forever. Physicists call such a coordinate ignorable or cyclic. Take a planet orbiting the Sun, describe it by its distance from the Sun and its angle around the Sun. The angle itself doesn't appear in the Lagrangian. Space looks the same at every angle around the Sun. Only the rate at which the angle sweeps does. Instantly, the momentum tied to that angle, which is the angular momentum, is conserved. And that single fact is Kepler's law that a planet sweeps out equal areas in equal times. It dropped out just from noticing a coordinate was missing, with no forces or torques computed. That's a small window onto next episode's theorem, asymmetry, here that the angle doesn't matter, producing a conservation law, here angular momentum.
This is starting to sound like a universal solvent. Is there anything the Lagrangian is actually bad at? Every method has a weak spot.
It has one, and naming it sharpens what the method really is. The clean Lagrangian, kinetic minus potential, quietly assumes that every force in your system comes from a potential energy, that the force can be written as the slope of some stored energy landscape. Gravity qualifies, a spring qualifies, electric and magnetic forces qualify. These are called conservative forces because they conserve the total mechanical energy. Nothing leaks away. But now put your sliding bead in honey or let air drag slow your thrown ball. Friction and drag don't come from a potential. They bleed energy off as heat, and heat isn't in your kinetic minus potential bookkeeping at all. Drop a friction force into the basic recipe and it simply doesn't fit. There's no potential energy whose slope gives you a drag that always opposes motion. So the pristine action principle, in its simplest form, stalls exactly when energy is being dissipated.
So friction breaks it. That feels like a serious limitation for everyday physics, where nothing slides forever.
It would be, except for a beautiful reframing. You can patch the method. There are bolt-on devices, like what's called a Rayleigh dissipation function, that let you carry drag along. But the deeper point is this. At the truly fundamental level, there is no friction. Friction isn't a basic force of nature. It's the blurred, summed-up effect of countless microscopic collisions. Your bead's atoms jostling the honey's atoms, handing kinetic energy off into invisible molecular motion. And every one of those microscopic interactions is conservative and does have a clean action. Friction is what conservative physics looks like after you've averaged over 1 trillion particles you chose not to track. So the Lagrangian isn't failing when it struggles with drag. It's telling you you've thrown away degrees of freedom. Zoom in far enough that nothing is hidden, and the action principle is once again exact and universal. It is cleanest precisely where physics is most fundamental, which is a hint about how deep it really goes.
That's a lovely inversion. Friction isn't a counterexample, it's a sign you've coarse-grained. Okay, so the practical case for the Lagrangian is energy scalars instead of force vectors, any coordinates you like, and constraints for free. But you keep hinting this is more than a computational convenience, that it's somehow deeper than Newton. What do you mean by deeper?
I mean two things, and they're the reason this idea sits at the center of physics rather than in a corner of it. The first is unity. Force equals mass times acceleration is a statement about particles being pushed. But the principle of least action is a template that reaches far beyond particles. You can write down an action, an accumulated something over a path or over space and time, for the electromagnetic field, and demanding it be stationary gives you Maxwell's equations. You can write an action for a relativistic particle, and stationary action gives you the correct relativistic motion. Einstein's theory of gravity, general relativity, is defined by an action. Quantum field theory, the framework behind particle physics, is built entirely on actions. Every fundamental theory we have is specified by writing down its action, its version of kinetic minus potential accumulated, and demanding that action be stationary. Physics, at its deepest, is not a list of forces. It's a collection of actions.
So, what is the action for this system has basically replaced what are the forces as the fundamental question across all of physics.
That's exactly the shift, and it's hard to overstate. When a physicist wants to propose a new theory, a new kind of particle, a new field, they don't write down forces, they write down an action, and the principle of stationary action generates all the equations of motion for them. The action is the DNA of a physical theory. Everything else unfolds from it. And that leads to the second deep thing, which is maybe the most beautiful payoff of the whole framework. The action format is exactly what lets you connect symmetries to conservation laws. There's a profound result, we'll give it its own episode because it deserves one, that says every continuous symmetry of the action corresponds to a conserved quantity. If the action doesn't care where you are in space, momentum is conserved. If it doesn't care when you do the experiment, energy is conserved. If it doesn't care which direction you face, angular momentum is conserved. That bridge between symmetry and conservation is called Noether's theorem, and it lives natively in this action language. It's essentially invisible from the force point of view.
You keep calling this a whole reorganization of mechanics. Is the Lagrangian the only such reformulation, or are there others?
There's a close sibling worth knowing because it's the bridge to quantum mechanics, the Hamiltonian. You get it by a mathematical repackaging of the Lagrangian that puts position and momentum on an equal footing, describing the system as a single point drifting through an abstract space of all possible positions and momenta, called phase space. And here's a satisfying twist. While the Lagrangian is kinetic minus potential, the Hamiltonian usually comes out as kinetic plus potential. The total energy, the very thing your instinct reached for at the start. So the sum you wanted wasn't wrong, it was just the star of the other formulation. The Lagrangian form shines for deriving equations and for relativity and field theory. The Hamiltonian form is the one that carries most directly into the quantum world. In fact, the Hamiltonian, the total energy written as an operator, sits right at the heart of the Schrödinger equation, which we'll meet in another tutorial. Two great reformulations of Newton, Lagrangian and Hamiltonian, two languages for one mechanics, each opening a different door, one toward fields and relativity, the other toward the quantum.
That's a beautiful hook for next time. But before we get there, you promised we'd come back to my rock, the uncomfortable part. This really does sound like the particle checks all paths and picks the best. You said there's a real resolution. I want it.
You've earned it. And there are two layers to the answer. One that dissolves the mysticism, and one that, remarkably, makes it deeper than you expected in a completely different way. The first layer, the principle of stationary action, despite sounding global and teleological, as if the particle surveys whole futures, is exactly mathematically equivalent to the local Euler-Lagrange equation, which is utterly humble and step-by-step. The Euler-Lagrange equation just says, at each instant, given where you are and how you're moving right now, here's your acceleration for the next instant. No looking ahead, no shopping around, no knowledge of the end point. Just local, moment-to-moment marching, identical in spirit to Newton. So the grand, nature chooses the best path statement, and the mundane, the particle just responds to its local conditions statement, are two faces of the identical mathematics. The global-sounding version is a theorem about the local one, not a claim that the rock deliberates. That should ease the discomfort entirely.
That does ease it. The picks the best path language is just a global summary of ordinary local step-by-step motion. But you said there's a second layer that makes it stranger, not tamer.
I did, and it's where this whole idea stops being a mere reformulation and reveals it was pointing at something profound the entire time. The second layer is quantum. Around the middle of the last century, Richard Feynman asked what least action really means down at the quantum level, where particles genuinely don't follow single definite paths. And what he found is staggering. A quantum particle, going from here to there, in a real sense does explore every possible path at once. Every path contributes, each carrying a kind of quantum phase, a little rotating arrow whose turning is set by that path's action. And when you add up the contributions from all the paths, something remarkable happens. For most paths, the neighbors have wildly different actions, so their little arrows point every which way and cancel out. But near the path of stationary action, neighboring paths have almost the same action. Because it's stationary, flat, remember, so their arrows point nearly the same way and add up powerfully, reinforcing. So the classical path, the least action path, is simply where all the quantum contributions constructively pile up. It's the path that survives the interference.
So the reason the rock appears to pick the least action path is that quantum mechanically, it really does try all of them. And least action is exactly the path where all those tries add up instead of cancelling out.
That is precisely it, and it's one of the most satisfying resolutions in all of physics. The teleology you were rightly suspicious of turns out to be real but not mystical. It's interference. The particle doesn't foresee the best path. It samples all paths, and the mathematics of adding up their quantum phases makes the stationary action path the one that stands out. So, least action, which started as a slightly eerie classical principle about nature being economical, turns out to be the shadow cast by quantum mechanics onto the everyday world. The classical principle of least action is what quantum path exploration looks like when you stand far enough back. Your rock objection wasn't a confusion to be corrected. It was a door to the deepest layer of the idea.
That's remarkable. The thing that looked like a philosophical curiosity is actually where classical physics quietly touches the quantum. Let me try to hold the whole arc. We started because force equals mass times acceleration gets clumsy with constraints and awkward coordinates, drowning you in forces you don't care about. So we switched from forces to energy and built the Lagrangian, kinetic minus potential, just a number. We accumulated it along a path to get the action and stated the principle. Nature follows the path of stationary, usually least, action, demanding that flatness gives the Euler-Lagrange equation, which reproduces Newton exactly for a particle, but works in any coordinates, killing constraint forces. And the whole action language turns out to be how all of modern physics is written, the natural home of Noether's symmetry conservation bridge, and, through Feynman, the classical shadow of quantum particles exploring every path.
That's the entire arc, and the thing I'd want you to carry out of it is the change of question. Newton taught us to ask, what are the forces and how do they push things around? Lagrange and those after him taught us to ask, what is the action and what makes it stationary? And that second question turned out to be the more powerful one, more flexible in practice because energy scalars beat force vectors and constraints come for free, and more profound in principle because it's the language of every fundamental theory, the seat of the deep link between symmetry and conservation, and the classical face of quantum reality. Force equals mass times acceleration is a magnificent tool, but least action is closer to how the universe actually seems to be organized.
From what pushes it to what does it minimize? Thanks for making that switch feel not just useful but inevitable. Next time we'll follow the thread you dangled, Noether's theorem, the astonishing fact that every symmetry of the action hands you a conservation law, that the reason energy and momentum are conserved at all is that the laws of physics don't care where or when you test them. For now, nature is economical, the currency is the action, and every path a system doesn't take is one it quietly tried and let cancel away.